Hey there. Let's talk about representing binary numbers with fractions in scientific notation. Why would you need to do this? Probably the best use that I can think of off the top of my head is being able to represent binary numbers with fractions inside your machine in a format known as IEEE 754. This video is not about IEEE 754. It's just a crucial step before you can represent numbers inside your machine using IEEE 754. Okay, so first off, let me just show you a little bit here about scientific notation. So you probably have seen something like this before where it's like 8.3873, and then you'll see like a multiplier times 10 to the fifth power, right? I can't really type this out very well, so maybe I could just draw it for a second, 8.54 times 10 to the fifth power, right? That's what I'm trying to convey. But anyway, so about scientific notation itself, it's standardized so that it's easier to use and that it's, it's just like faster for everyone to understand and there's less confusion. Part of the standard is that you always want to have a number on the left side of the multiplier that is between 1 and 9 inclusive. You don't ever actually want to have a 0 there. That would be bad. You don't want to have a 10 or anything greater. That would also be bad. You just want to have 1, 2, 3, 4, 5, 6, 7, 8, 9 on the left side. And then on the fractional side, you want to have a number that just kind of like helps you represent the entire original number without losing precision. And then on the right side, you want a number, let's say like x to the y power, where x is the base of the number system you're working in. So this is decimal. The base for decimal is 10. So we're going to say 10 to the something power. What is the power? The power here helps you understand how big or small the number on the left really is. That's kind of one of the benefits of scientific notation. It seems to help you understand a little bit more of how big or how small a number is, rather than exactly down to the last digit. What is the number precisely? So we could say for now it focuses more on largeness or smallness than preciseness. What number are we actually representing with this in scientific notation? Well, times 10 to the fifth power just means move the decimal point over a certain number of times. So, that's why we have 10 to the something power, because we're in base 10. Every time you go left or right in a base 10 number, you're looking at a different number that has a factor of 10 for its strength in either direction, like multiply by 10, multiply by 10, multiply by 10, or divide by 10, divide by 10, divide by 10 in the other direction. So this means we want to move the decimal point 5 times to the right to increase the strength of the number times 5. So 1, 2, 3, 4, 5. If we put the decimal number there, then this is the number we were going to represent originally. So if somebody says, hey, give me this number, 838730, and put it in scientific notation, then your first instinct is to say, all right, let's type that number out, and we'll put like a .0 there, and we'll move the decimal point over until there's only one digit. And it's somewhere between a 1 and a 9 inclusive. How many times do we have to move this over? 1, 2, 3, 4, 5 times over in order to get the decimal point there. So that means it's going to be this times 10 to the fifth power, because we moved it over 5 times. And you can see that's the original number that I showed you. These zeros at the very end, they don't actually mean anything, so we can omit them. Probably a smarter idea to omit them. And that's why we see numbers that way. Okay, so keep that in mind. There's only one digit. Let's maybe do like another practice number here. I have a couple practice numbers written down already. Let's see. So we'll start with this number, a huge, gigantic number. Just to practice, if we copy paste this down to the next line, and then we decide, all right, how many times do we need to move the decimal point to get the decimal point right there, so that the 2 is the first number. Remember, 1 to 9 inclusive. So I'll use 2 decimal points so I can count more easily. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that means I did 13 moves. I'll put 13 right here so I don't forget, times 10 to the 13th power. And the 13 is positive because when we're looking at the scientifically notated format of the same number, 2 point something is way smaller than the original number. So we want the scientifically notated format or form to get bigger in order to reach this number. So that means 10 times, times 10 to a positive number. Positive means it'll be bigger in its original form. Okay, so now let's do another practice number. Let's do a number that's really, really, really small, like you're inside of inner space or something. So we start off with this number, and we still want to have a number between 1 and 9 inclusive before the decimal point. So if I rewrite it here, I really want to have 8 point something, because that's the first number that's bigger than 0 that I can see. So again, I'm using 2 decimal points so that it's easy for me to count. I'm going to go 1, 2, 3, 4, 5, 6, 7. I had to move it 7 times. So it's going to be -7 is going to be the exponent. So, something raised to the -7, it's still going to be 10 to the -7 that I multiply it by. So then I'll say get rid of the decimal point, and now this is the same number represented in scientific notation. It should have all the same digits. The decimal point basically should just be moved. Of course, when you represent in scientific notation, depending on what standard you're working with, you might actually omit some of the numbers at the very end of the fraction here, but that's why we say this is kind of more to impress upon you the smallness or largeness of a number rather than represent the number exactly precisely. Okay, so we got that. 2 practices in there. How can we do this same exact concept in binary? Well, keep in mind in binary, binary is a base 2 number. This video is not about binary conversion as a whole number or binary with fraction. Let's just pretend that we already know how to do that. And we have a binary number to start off with. So let me grab my example number here. Suppose we have some kind of a binary number with a fraction, which you can do. If you don't understand how to do this part yet, from decimal with a fraction to binary with a fraction, or back and forth, see my other videos. For now, we'll assume you can do this. So how can we get this in scientific notation? So the first thing we have to understand is that it's going to be, some number times a base to an exponent, right? Because that was the format we used before. The number should only start with a 1. It should never even start with a 0. Remember, in binary, we can only use 1s and 0s. Before I said, here, let me just show you this real fast again. Before I said the starting number has to be 1 through 9 inclusive, that was because in decimal we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we would just ignore the 0. So it would only be, only use, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, but in binary, I'll put like the character set, like the available characters we can use to represent the numbers in decimal. So in binary, the char set that we can use is just, a 0 and a 1 only. But the same rule applies, only use everything but the 0. So that means only use the 1. So that means the first number always has to be 1. It has to be always 1 dot something for our purposes to represent the same number in scientific notation. So it's going to be this, and obviously that 1 has to be it. It cannot ever be a 0. So I'm going to put the decimal point there, and then I'm just going to count, like how much did I actually move the decimal point? I moved it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, just 15. Just 15, not 16. So I'm going to put times something to the 15th power and remove that other decimal point. And then the base is 2, so it's going to be 2 to the 15th power. So now, maybe I should move that up a little bit. We know how to represent this gigantic number in scientific notation. It's going to look a little smaller, but then the times base to the 15th power is going to help us understand how big it is. Oh, it's like pretty big. Let's do the same thing backwards. Let's say that we wanted to start off with a very, very small number. So it's like, a 0 point something in binary. So you can imagine if this is like 1/2, 1/4, 1/8, 16, 32, 64, 128, 256, that's probably going to be a number that's no bigger than, or just like slightly bigger than 256. So it's going to be like kind of a small number, right? Well, we'll do the same thing. Just copy to another line and then make sure that the decimal point sits in a place where there's always a 1 at the start. And then just count the number of times you moved the number. Oh, I guess before we would have possibly deleted numbers on the right if we were going to reduce precision. In this case, after we count the numbers, we're going to remove everything to the left of the 1 so that the 1 is in the first position. And I'll just go ahead and do it. Okay, so how many times did we move it? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 times. So I'm going to put an 8 there just to remind myself that there will be an 8. I'll remove all the stuff at the beginning that doesn't matter anymore. And it's going to be times 2, because that's our base, to the 8th power. But the original number is a lot smaller than the scientifically notated number looks. So that means we have to put a -8. Because remember, when you say times, let me just show you this on a calculator. When we say, let's go back to decimal for a second. If we say 10 to the 5th power, then you know that we're just basically adding 4 zeros, right? So like we have 5 total zeros, so we're adding 4 zeros to the 10. But if we did to the -5 power, we're going to be like dividing it by 10 a bunch of times. So instead of multiplying it by 10 for a total of 5 times, we're going to divide by 10. So then the number gets really, really, really small. So that means when we say 2 to the -8 power, we're going to be dividing it by 2 that many times. And so we end up with a really, really, really small number. Isn't that what I kind of said? Let's see. I mean, like, not exactly, but, you know, it's like 0.003 and then some numbers after that. Didn't I say 1 divided by 256? It's 0.003 and then some numbers. So this number is just a little bit bigger than 0.0039. Let's see how much bigger it is. 0.3625. What? Oh, because I'm not including the part on the left that we'll multiply it by. So if I did some like binary up here and I was in binary mode, then it would probably make more sense. It ended up being exactly the same exact number. That's why I was confused, because if we just type that part on the right side, then it really is going to be 1/256. Anyway, long story short, we have this number here, the fractional part, and then we were going to multiply it by 2 to the something power. Notice something in particular that I'm doing, which is probably my mistake, but I kind of like doing it this way. Notice how the left part is in binary and the right part is in decimal. There's no number 2 in binary or no number 8 in binary. So when it comes to converting numbers like this to scientific notation so that you can convert a binary number to IEEE floating point number, this is as far as you really need to go. But if you truly want to represent a binary number in scientific notation, then you should also convert all of the relevant parts. So how do we represent the number 2 in binary? It's going to be 1, 0. How do we represent the number 8 in binary? It's going to be 1, 2, 4, 8. It's going to be that. So, this big number times 10 in binary is still the number 2 to the something power. The -1000 in binary power is going to be, 8, the -8 power. So this is great if you just want to write an entire number in scientific notation. But, in probably my next video, when we talk about IEEE 754 notation, this is as far as you really need to go, because we'll basically just be converting this this -8 number into a whole number in binary and then putting that somewhere. But so just forget about this for now. Keep in mind, this is how far you have to go if you want to go to IEEE. If you only want to be in pure binary, then this is what it would look like. Okay, that's it. I think that's all the example I have for you today in this video. Thank you so much for watching. I hope you learned a little bit and had a little bit of fun. See you in the next video. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.